Welcome to week 2 of our online business calculus class. By the time you get ready to watch this video, you should have completed the Chapter 11 exam on MyMathLab. You should have also completed the first 3 pages of notes for section 12.1. In this video, I'm going to be working through example 5 and also example 7 and 8. So let's begin in section 12.1 with example 5. At this point, you have already learned the power rule, the constant rule, the constant multiple rule, and the sum and difference rule for differentiation. And by the way, aren't you thankful for these shortcuts after having been through the x plus h definition? The differentiation rules make life much easier. So in example 5, we're going to be applying a combination of all the rules that you've learned. So let's consider the function in part A. Y equals 6x cubed plus 15x squared. We are to find the first derivative of the given function. We can denote this in several ways. One is to call it dy over dx. Another way is simply to call it y prime. We'll examine a variety of different notations as we work these examples. The derivative of y with respect to x can be applied term by term. So I'm going to differentiate the first term, 6x cubed. Since we have a constant multiplier times the power of x, we're going to filter that constant through to the derivative, and then we're going to apply the power rule to x cubed. So we bring the exponent down in front, and then we decrease the original exponent by 1. We're going to do the same technique to the second term. So we record that constant multiplier in the derivative, and then we apply the power rule to x squared. So the exponent becomes the coefficient, and then we decrease the exponent by 1. So the original exponent was 2. If we subtract 1 from that, our new exponent is 1. When we simplify, we end up with 18x squared plus 30x. So that is the derivative of our function. Again, it's much easier and much more convenient than differentiating by definition. Let's move on to example B. We're also going to be applying the same techniques, that is differentiating term by term and using the power rule. However, it's helpful on this one to rewrite the original function so that t has powers on it. We're going to get rid of that radical. We're also going to get rid of that t in the denominator. So notice the notation here. I'm not differentiating yet. I'm just rewriting the function. So I'm going to denote that as p of t. The first term is in a good form for differentiation, but the second term we can rewrite as minus 6t to the 1/2 power. Anytime you see a square root, it's equivalent to a 1/2 power. For the last term, we can write that as 5t to the negative 1. Now the function's in a form where we can differentiate term by term using all of our rules. Let's denote that we're actually taking the derivative by denoting it p prime of t. As we did on the previous problem, we're going to take all of those constant multipliers through to the derivative. Then we can apply the power rule to t. So the power comes down in front, and then we decrease the original by 1. Same technique is applied to the second term. We have our constant multiplier. The original power comes down to the left as a coefficient, and then we're going to subtract 1 from the exponent. 1/2 minus 1, you can think 1/2 minus 2 over 2. That would give me exponent negative 1/2. Same thing for the third term. We have coefficient 5. The power comes down in front. The power was negative 1. And then we're going to decrease the exponent by 1. Negative 1 minus 1 gives us a new exponent, negative 2. Let's simplify this a bit by multiplying those coefficients. And then let's attempt to express this in the same notation that the original p of t was given. So our p prime of t can be written 48t cubed minus, now 3t to the negative 1/2. Notice that negative exponent Anytime you have a negative exponent, it sends the expression to the opposite place in the fraction. Sort of like what we did with this term here. It was originally a t in the denominator, and we took it out of the denominator and gave it a negative exponent. So I'm going to do just the opposite for this term. I'm going to take the t to the negative 1/2 and put it in the denominator, and then give it a positive exponent. So I would end up with 3 over t to the 1/2. But we also know t to the 1/2 is equivalent to square root of t. For that last term, the coefficient is -5, and we'll move that t to the -2 in the denominator and give it a positive exponent. So we have successfully found the derivative of the function p. On example C, like we did on example B, we're going to have to clean up the function a little bit before we differentiate. Again, I'm going to denote this by naming this function f of x. That way I'll remember at what point I actually began finding the derivative. I cannot differentiate individual terms in a quotient like this. We'll learn later on something called the quotient rule, but for now, we want to split up that fraction. I'm going to take each term in the numerator and put it over the denominator. That way I'll have separate and distinct terms that I can differentiate term by term. When we simplify, we end up with x squared plus, now don't forget, square root of x is the same thing as x to the 1/2. So what we notice here is that we are dividing like bases. When we divide like bases, we subtract the exponents. So if I take the exponent on top, 1/2, minus the exponent on the bottom, 1, 1/2 minus 1 gives me -1/2. So I can simplify that to be 3x to the -1/2. Now it's in a form that's good for differentiation. We can differentiate term by term, applying all of our rules as we go. I'm going to denote that we're actually changing the operation and we're finding the derivative by naming this function f prime of x. So the derivative of x squared becomes 2x. For the second term, we have constant multiplier 3 times exponent -1/2, and then we need to decrease the original exponent by 1. So we need to take -1/2 and subtract 1. -1/2 minus 1 is the same thing as -1/2 minus 2 over 2. So we end up with -3 over 2. So to clean this one up, the first term is good to go. 3 times -1/2 is -3/2. And we can put that exponent, -3/2, into the denominator and make it positive. So that is the derivative of f. Notice on both of those examples, we first had to do a little bit of algebra to the function before we found the derivative. The same is going to be true on example D. On example D, we will eventually learn how to differentiate this directly using something called the chain rule. However, until we learn that, we want each of our functions simply to be expressed as the sum or difference of multiple terms. So before I differentiate, I'm going to prime this function so that it's in a good format to apply the rules that we know to this point. So I'm just going to multiply everything out. If we have 4x squared minus 3x quantity squared, it simply means we're multiplying that binomial by itself twice. So we can FOIL. The product of our first two terms is 16x to the 4th. For the outside terms, we end up with minus 12x cubed, and we get the same thing for our inside terms. And the last terms, we have plus 9x squared. If I combine like terms in the middle, we have an equivalent function here to the original. It's just in a multiplied out form. This is the one that I want to differentiate. So we're ready to find the derivative. We're going to make sure and denote the point at which we find the derivative because that fundamentally changes the function. Applying our power rule and our constant multiple rule term by term, we have 16 times 4x cubed minus coefficient 24 times power rule 3x squared plus coefficient 9 times derivative 2x to the 1st. When we simplify, we just have to go back and multiply those coefficients. So we have 64x cubed minus, let's see, 72x squared plus 18x. So remember those algebraic simplification techniques before you differentiate. Now, in the next portion of your notes, you're going to be learning about marginals. Remember that a marginal is simply another word for finding a derivative. So marginal cost will mean the derivative of the cost function. Marginal revenue will be the derivative of the revenue function. Now, pause the video, read through the next information, and when you get ready to work example 7, you can restart the video and I'll work through it together with you. Okay, once you're ready to work example 7, here we go. We have the demand function for a certain product is given by P equals 50,000 minus Q over 25,000. Find the marginal revenue when Q equals 10,000 units and P is in dollars. So first of all, notice we are given the demand function and we're asked for marginal revenue. Remember, marginal is a fancy word for derivative. And we're attempting to differentiate the revenue function, which I do not have at this point. So our problem is to find the derivative of revenue with respect to Q. So before I can differentiate revenue, I have to define my revenue function. The revenue function, as you read previously in the notes, is simply quantity times price. Our price is given right here in this function. So we're going to have quantity Q times 50,000 minus Q divided by 25,000. We're going to do a little algebra to simplify this function before we differentiate. Let's begin with that fraction. Let's divide each term in the numerator by that denominator. So we have 50,000 divided by 25,000 minus Q divided by 25,000. Then we can simplify and distribute this Q to each term and we'll have our revenue function. So R of Q, 50,000 divided by 25,000 is 2. Multiply that by Q to get term 2Q. And then we have Q times negative Q over 25,000. Let's write this, minus 1 over 25,000 times Q squared, so that it will be easy to differentiate. Now we're ready to find the marginal revenue. Marginal revenue is simply the derivative of your revenue function. All right, so we're going to find R prime of Q. So the derivative of 2 times Q is simply 2. For the next term, we're going to have coefficient negative 1 over 25,000 times derivative of Q squared, which is 2Q. When we simplify, we have derivative R prime of Q equals 2 minus, now if we want to reduce this fraction, 2 goes into itself once and 2 goes into 25,000, 12,500 times. So we can call this minus 1 over 12,500 times Q. So there is our marginal revenue function. Now the question says, what is the marginal revenue when Q is equal to 10,000? All we have to do is plug 10,000 in for Q. So we'll evaluate R prime of 10,000. So we have 2 minus 1 over 12,500 times 10,000. Now at this point I would pull out the calculator and let the calculator do the arithmetic. So we'll type it in as 2 minus 1 over 12,500 times 10,000. And we end up with 1.2 for our answer. So this would be $1.2 per unit. Or we could say $1.20 per unit. Thus, the next item sold at a sales of 10,000 will produce an additional revenue of about $1.20. Okay? Let's work example 8 as well. Suppose that the cost function for the product in example 7 is given by C of Q equals 2100 plus 0.25Q. where Q is between 0 and 30,000. Find the marginal profit from the production of the following numbers of units. So notice what we're looking for, marginal profit. Marginal, remember, means derivative. So I'm looking for the derivative of profit with respect to quantity Q. Now, before I differentiate my profit function, I have to write a profit function. We have, from the previous example, our revenue function, that was up here, and now we have our cost function. Remember that profit is revenue minus cost. So we have our R of Q minus C of Q. In example 7, we found out that R of Q is 2Q minus 1 over 25,000 times Q squared. There's my revenue function. Now I'm going to subtract the given cost function from this problem. That's 2,100 plus 0.25Q. So in simplifying our profit function, we need to distribute this negative to each term and combine like terms. Notice after I distribute that negative, I'm going to have like terms here and here. We'll have 2 minus 0.25Q. We can simplify that as 1.75Q. We'll write our negative 1 over 25,000 Q squared next. And then don't forget we had that minus 2,100. Once we get our profit function, then we can find marginal profit. Remember, marginal profit is simply the derivative of our profit function. So differentiating P of Q, we end up with 1.75 minus coefficient 1 over 25,000 times derivative with the power rule here, 2Q. And don't forget the derivative of a constant is 0, so the derivative of 2,100 is 0. If, again, we want to simplify like we did on the previous problem, 2 goes into itself once, 2 goes into 25,000, 12,500 times. So our simplified marginal profit function is 1.75 minus 1 over 12,500 times Q. So there's our marginal profit function. Once I have that, I can do all kinds of analysis. The next question says, at Q equals 15,000, the marginal profit is what? Well, that simply means I'm going to plug in 15,000 units for Q and evaluate that specific number. So we have 1.75 minus 1 over 12,500 times 15,000. At this point, I would simply plug it into the calculator. So we have 1.75 minus 1 over 12,500 times 15,000. When we evaluate that, we get 0.55. That's $0.55 per unit, or 55 cents per unit. For example B and C, I'm simply going to plug each of these numbers into our marginal profit function and calculate that number. And again, you can just type those into your calculator. I bet you can take it from there. Thanks for listening and keep working hard.